want to evaluate an indefinite integral as a power series. So we're going to start with our integral, which is t over 1 minus t to the 6th dt for part A here. So to integrate or to evaluate this as a power series, we need to find a power series representation for the function that we're integrating and then just take its antiderivative. So the first thing you want to notice is that we can write this in terms of power series we know. We should write this as integral of t times 1 over 1 minus t to the 6th dt. Because this part right here, the 1 over 1 minus t to the 6th, looks a lot like our standard power series that we know. So you should know that 1 over 1 minus x is the sum from n equals 0 to infinity of x to the n for the radius -1 to 1. So we have essentially that, except we're replacing t to the 6th, or we're replacing x with t to the 6th. And then we're going to multiply that entire power series by t. So first we want to say that 1 over 1 minus t to the 6th is going to be the sum from n equals 0 to infinity of t to the 6th n. Because if you replace this x here with t to the 6th, we get t to the 6th to the n, which is t to the 6th n. So then if we multiply through by t, we can just say then that that is from n equals 0 to infinity t to the 6th n plus 1, because we're just multiplying another t into that. So that takes care of everything here. So now we want to take the antiderivative of that. So remember that when we take the antiderivative, we can just take the antiderivative of our sum end. Remember that you have to add a c, though, constant of integration. So we get then that the integral of t over 1 minus t to the 6th dt is going to be the integral of this here. So we're going to get c plus, we have our constant of integration. So we're still going to have the sum from n equals 0 to infinity. And we're just going to take the antiderivative of that term right there. So the antiderivative of t to a power is just, power over integrals. Take power plus 1, divide by it. So we're going to get t to the 6n plus 2 over 6n plus 2 by power rule. So right here, that is our power series representation of this indefinite integral. So that was the question for part A. For part B, it just asks us what is the radius of convergence. Well, recall that the radius of convergence, when you take the, you have a theorem that you did in your book or in class that says if you take the derivative or antiderivative of a power series, it doesn't change its radius of convergence. So the integral of this should have the same radius of convergence as this part up here. Now this part, we did substitute t to the 6th, so our original, this power series up here has the radius of convergence of 1 because x has to be in between -1 and 1. So for here, now we're replacing x with t to the 6th, so we say that t to the 6th has to be in between -1 and 1. In other words, you can write that like that. The absolute value of t to the 6th has to be less than 1. Okay, and it should be obvious then that's still the same thing as saying t is in between -1 and 1. Because obviously if it's -1, if we raise it to the 6th, it becomes 1, so that's a bound there, and +1 is the upper bound. So our radius of convergence is 1 still. Okay, and part C was to find the a certain number of constants here of integration, or not the constants of integration, sorry, the constants that are multiplied times the terms of the power series. So remember that the power series of the form, you have the variable part and then you have everything else. So let me rewrite this real quickly in a form that's easier to recognize what this question is asking. This is 1 over, so it's 1 over 6n plus 2 times t to the 6n plus 2. So every term of this series is going to be coefficient and power of t. So we just need to figure out what these coefficients are. So this is just a matter of plugging the numbers, so I'm going to go through these quickly. So c sub 0, so that means the first constant, or the first coefficient I should say. So if you plug in 0 for n, you get 1/2. So what else do we need here? We need c1, c2, 7, 8, 9, and 10. So we just plug in those values in for n. So c1 would be 1/8. c2 would be 1/14. 7, so that would be 42 plus 2, so we get 1/44. 8 would then be 1/50. You should see the pattern here because the n is times 6. If you have consecutive coefficients, their denominator is always going up by 6. So you can say this is 1/56 and 1/62. So this is how we represent an integral by using a power series.